Good morning, everyone. My name is William Reid, and this work has been done as a collaboration between the University of Sydney and the University of Technology, Sydney. And what I'd like to talk about today is using a hierarchical structure for sampling-based planning for reconfigurable mobile robots. So I'd like to introduce you to the Mammoth rover. Mammoth is a Martian analog exploration rover. It is a high degree of freedom reconfigurable mobile robot. Mammoth is an omnidirectional system. It may drive in the X and Y directions, but it may also raise and lower its body. In addition, it can reconfigure its orientation. So as you see here, it's changing its yaw, and it may also reconfigure its pitch and roll. Now, we designed this robot to expose lots of different mobility modes. Here you can actually see it reconfiguring its footprint from a compact state to a more nominal, stable state. So what we'd like to do is develop a motion planner that exploits all these different reconfigurabilities and different mobility modes to even expose some maneuvers like this one, which is a clambering maneuver over obstacles. And so to do this, we define this planning problem where we have our reconfigurable mobile robot in a start configuration, and we want to get to a goal configuration represented by the star. And in this environment that we've got a bunch of obstacles represented by these white boxes, and we assume an arc length function, which is, in this case, we're using a mechanical work approximation, the amount of mechanical work it takes to get from one sample to another. And our objective is to find an optimal solution to the problem. Now, we have implemented a hierarchical sampling-based planner, which utilizes the state-of-the-art fast-marching tree star algorithm. And what we've done is we attempt to reuse information from within a subspace, and as the hierarchy progresses, go towards the full space. So we build upon the fast-marching tree star algorithm, which incrementally expands a series of sets. And like PRM star, it initially samples a large number of nodes within in this case, an R2 space. And like an RRT star algorithm, attempts to build a tree through the space. So we use this one expansion to formulate a tree such as this. And this work has been done by, the FMT star was done by Janssen et al., and then this was iterated on by Starek et al. In 2015 to a bidirectional fast-matching tree. And basically what this is doing is growing two fast-matching trees from the goal in initial configurations, and they propose different termination conditions. We propose a new termination condition called the exhaustive termination condition, where we find a termination and then we continue to search by finding multiple candidate paths, and we use this in our hierarchical framework. So this leads us to our hierarchical algorithm. So initially we manually select a subspace. In this case, we select the translational space of the robot, and we perform a bidirectional fast-matching tree search through this space with this exhaustive termination condition. From this, we get multiple feasible paths. Well, we may get multiple feasible paths, and we then take these return solutions and bias the sampling within the full space of the robot, leading us to a solution that looks something like this, where you can see a simulated Mammoth rover reconfiguring itself between these tight, narrow passageways and getting to the end configuration. Now, to do this, we use a couple of tuning parameters within our algorithm. In the initial subspace search, we have this parameter called a singe radius. which is used for the exhaustive termination condition. And this, what this does is it singes all the nodes around a termination collision so that a path, an alternative path is not close to this initial path. And then we also have two other tuning parameters in our full space. One we call the tunnel radius, which defines how focused the search is around the biased paths that we found. And then we have a uniform sampling density parameter, which allows us to obey the asymptotic optimality guarantees presented in the FMT star paper. So when does this method work? Well, it works quite well when you've got this subdimensional structure to your problem, and we've noticed this working quite well for the Mammoth rover, and we conjecture that it would work well for this class of reconfigurable mobile robots. Now, for asymptotic optimality, we have taken the proof of asymptotic optimality for FMT star and the observation made by the authors regarding non-uniform sampling densities, and we incorporate this tuning parameter L. This tuning parameter L, and we make sure that with L probability we sample in the uniform. From a uniform distribution, so that if we still can maintain these asymptotic optimality guarantees. And for the radial case of FMT star, we basically incorporate these two terms. So we've run a series of experiments with this algorithm using the Mammoth rover, and we consider an 8 degree of freedom configurations. 8 degree of freedom planning space. And this space incorporates the translation of the vehicle, the yaw of the vehicle, as well as its reconfigurable footprint represented by each of its hip actuators. We also incorporate a static stability constraint to make sure that the robot doesn't fall over. Now, we've run these experiments in a variety of different environments, trying to trick the planner. First off, we have this gauntlet environment, which is a maze-like terrain with lots of cluttered obstacles and even a tunnel that the Mammoth rover has to go down towards the ground and go through. And then this alternatives case, which presents two different alternatives in the subspace, and when it explores in the full space, it finds that this alternative is quite energy intensive compared to going around these block obstacles. And also to demonstrate that we can expose this clambering maneuver through the space, we have this steps environment. And we've implemented all of this in OMPL, and we've benchmarked it against FMT star, BFMT star, RRT star, and RRT Connect. And the results demonstrate first off, they demonstrate that the FMT star variants improve the path quality considerably compared to RRT star, but we also see an improvement in the path quality for both the gauntlet alternatives environments with the hierarchical planner, especially when we have a limited number of nodes to use. Now, in conclusion, what we're doing here is we're reusing information from a initial exploration of a subspace, and we're trying to exploit these essential subspaces for a reconfigurable mobile robot. We've noticed from our experimental results that we get higher quality plans with equivalent computational resources, and we've demonstrated this in simulation, and I would like to I will show you it's working in practice with the actual robot. For future work, we'd like to incorporate a traversability cost that's used by a lot of planners for Mars rovers, and we would like to validate our cost function that we've used for these physical experiments. What we'd also like to do is incorporate more levels into the hierarchy. So currently we only have these two levels, and we'd like to exploit exploit, say, motion primitives as an intermediate level. Now, for the dirty laundry, we're attempting to, we're hand tuning a lot of these parameters, and we'd like an automatic way of doing this. And we'd also like to use techniques similar to the one previously presented of automatically finding a subspace to plan in to perform this rapid search at the beginning of the planner. And we're currently, well, as I said, we're currently limited to 2 levels of planning. So here you can see, this is recent work that we've done to expand our work, and you can see the results of HBFMT star running with the actual rover. And it successfully traverses around each of these box obstacles, and at the same time maintaining a static stability. And you get a lot of exotic reconfigurations because you get a lot of exotic reconfigurations, which is what we were attempting to find at the beginning, setting out with this problem. And here, with this example, we demonstrate the clambering maneuvers that the vehicle is capable of. And these clambering maneuvers we've enabled by saying if the wheel is in collision with an obstacle or a leg is in collision with an obstacle, we will resample that configuration with that leg raised, which seems to work quite effectively with this FMT star variant. And this example demonstrates our capability of breaking or virtually breaking some of the actuators. So in this case, we've broken the front 2 hip actuators, and we can see that the vehicle is still able to find a solution by keeping these 2 hip actuators stationary. And what we've actually found is we get lower cost paths when we constrain the planner to do such a task. And this is what we've been thinking about doing, is using this for further levels of the hierarchy. So, thank you.
Yes, question from. Yeah.
Yeah, so I mean, it's really different.
Thank you.
The whole idea of subspace sampling is really true efficiency. Thank you. So there are some. I don't know if this works. There are some parameters that you have mentioned, and you're doing some hand tuning. In the paper, there's also some comparison as to, like, even if you change the parameters, it's kind of robust.
Yeah.
But one wonders whether that's about the cost function. The cost function is energy, and it almost seems like the space is very similar in terms of the energy cost. So there's a lot of trajectories that are very similar to each other. So maybe the parameters, like the size of the balls, for example, that you look for resampling, don't matter in the energy cost function. I wonder if you've gotten a chance to actually look at other cost functions to see if there will be sharp differences in terms of tuning parameters.
Yeah. So from these experimental results that we're running, we're trying to validate our cost function. It is an approximation of mechanical work, and what we found, and one of the items of future work that we really want to focus on, is incorporating this ankle steering actuator into the planner, and that's something that we've found that doesn't agree with the cost function, which costs us a lot of energy. So I agree. We do need to modify this cost function to become more representative of the actual vehicle, and whether or not that could be incorporated into tuning these parameters, I agree that would be an interesting topic for work.
A question? No? Yes.
Just a wild question. Other than Mars, do you have any plans to try this in other environments, and can it climb steps?
There's a lot of farms in Australia, and we've taken this out to a farm for going up and down crop rows, and it reconfiguring itself and going in between trees. There's also been interest from mining groups. There's a lot of mining in Australia as well, it turns out.
Just sidewalks. Can it step up to a sidewalk?
Sure. Yeah. If in this case it knows its environment, but if it's got this environment model, it can step up onto a sidewalk. Sure.
Okay, so thank you.
Okay,
We can
thanks very much.
thank again all of the speakers and respondents.